So today's speaker is Fei Li from Department of Computer Science here at Mason, and he's going to talk to us about max-cut problem and relationship to quantum computing. So welcome.
Okay, thank you, Maria. And this is my first presentation on quantum algorithms. So I would like to introduce the algorithm approaches to the max-cut problem, which is quite famous. And also I would like to introduce my understanding about those algorithms. And in this presentation, I'm going to present two classic algorithms and one quantum algorithms. And I will try the best to deliver my understanding and also some of the questions that I may have. And I would like to discuss with you for possible future collaboration to deal with them. And the materials of this presentation includes a few algorithms from the computer science algorithm books and also the quantum algorithm books, and also the classic paper, which is a quantum approximation optimization algorithm published in 2014. And this paper is the first paper talking about approximation algorithms using quantum computers. And that opens a new door for us to study NP-hard problems. And also, if you have any questions, you can either ask me online or you can send any questions through the chat window. And I will try to deliver as much as I can to make it clear. Okay. So the presentation consists of 4 parts, and I'm going to talk about some basic knowledge. The first algorithm, I mean the classic algorithm, approximation algorithm, the second algorithm, classic one, and the last one, which are quantum algorithm. The motivation of introducing the first 2 classic algorithms is that I would like to compare the classic ones with the quantum algorithm ones. I know that there exists an essential difference between these algorithms, and it is quite interesting to study the underlying motivation as well as the underlying reasons why these algorithms perform quite differently. So I'm going to talk about the problem. I'm going to talk about the basics and the problem of the max-cut. I apologize that I couldn't draw the figures using some beautiful tools, but I drew it on the paper and I hope that my handwriting is clear to you. So we know that whenever we have computational models and we would like to design algorithms so that these algorithms are the mechanical steps to implement the ideas and try to get an output based on the input that we have given to it. So the first computational model, at least to the computer scientist, is the universal Turing machine model. You have an infinite size tape and you have a header. The header reads the information from this tape, and the header could move to the left or to the right based on the instructions given in the table, the stored table. And the table itself specifies the algorithm. And if we have such kind of machine, and the first theoretical question is to study the power and weakness of such a model. So we know that based on the power of the computational model, we classify the problems that we are facing into several categories. And the first one is the, among all the functions that we could calculate, the first one is computable functions that they could be computed, but some of them may not be computed using the classic Turing machine. So a subset of this computable function is the exponential time algorithms. So since like we have a table and then we would like to consider both the correctness of this model as well as the performance of this model, which is the efficiency. And we would like to consider the running time, the space required for this table. So if we have EXP, which is exponential time, algorithm, problems, it indicates a class of problems such that we need the total running time, which is exponential function. And within a subset of this, EXP is the P-space. P-space is the class of problem such that at any time that all the information needed is bounded by a polynomial space. And P-space, one example is more like a chess that we are playing. So we know that the size of this chess table is finite. It's a polynomial time of the, sorry, it's a polynomial time function. But if we have two players that actually if we would like to explore all the options for these two players, we could see that the options could be an exponential function. And NP is the concept that we are quite familiar with. And this is the set of classes, is a set of problems that we have a verifier, polynomial time verifier, a verifier for these problems. And within this set, there is the NPC is NP hat, or you could say like it is NP complete if you consider the decision problem. And there exists, let me see. There exists a conjecture saying that whether P equals to NP, but that is for now, that is we still don't know that. Okay, so give me 1 second. I'll look to make it to full screen. Okay. Sorry. So this is the all the boxes written in the blue ink. Right? They are the classical view from the computer scientist. And whether P equals to NP, this is still conjecture. And however, that with the development of the quantum algorithms, with the factoring algorithms, that people try to study the power and the weakness of the bounded error quantum polynomial time algorithms. So far that we still do not know whether the quantum algorithm can perform much better than the polynomial time algorithms. And factoring is a very special one, which is in between the class P and the class of NPC. Okay. So since like, this is the picture that there are several questions, open questions that we haven't answered yet. So if we know this one, then it would be, if you would like to prove that the BQP, which is bounded error quantum polynomial time algorithm, so you look at classes of problems. If you want to prove that BQP equals to NP, that is the same difficulty as the problem proving that P equals to NP. So if we do not want to do that, and then we need to think about that whether the BQP, such kind of problems, could be used to design approximation algorithms instead of, quantum computers could be used to design approximation algorithms, like what are the Turing machine. Okay. So here is the picture about the classic algorithm design. So for those NP hard problems that based on the conjecture P doesn't equals to NP, then we know that if we want to satisfy 3 criteria, like that is to find out the optimal solution of the problem, which is the optimality, to make the algorithm efficient such that the running time is a polynomial time function, and also to guard the worst case guarantees such that we are dealing with the problem in the general case. So for all these 3 measures, we couldn't satisfy all of them, subject to P doesn't equals to NP. So we have to pick up 2 measures to optimize. And for here, when we design approximation algorithms, we pick up the 2, which are running time and optimality. That means like if we would like to have an efficient algorithm, a polynomial time algorithm, and we expect that the algorithm performance is not optimal, but near optimal. And the gap between the solution found by our algorithm and the optimal solution, and this is the gap we would like to try to shrink. And we will introduce the approximation ratio, which is to reflect the ratio between these 2 values. And for the approximation algorithms, and like what is the exponential algorithm for such kind of problems, they are dealing with the general case. Say like they consider the worst case performance of the algorithm. The only issue is that whether we can design some polynomial time algorithm so that the performance is near the optimal one. And in order to define the gap, then here is the concept called the approximation ratio. So like if we have an algorithm, we select the approximation algorithm, which is efficient. So like this running time is a polynomial time algorithm. And it also works for the general case for all the instances of the problem, but the solution of this algorithm is not optimal. The solution, the performance of this algorithm is defined by the ratio between the algorithm performance and the optimal solution, solution, yeah. So this is the for the maximization problems that we would like to shrink this gap between the optimal solution and the algorithm one. And for the minimization, we just reverse the ratio. Actually, in most of this time that we don't care about which order we get the ratios, we only care about the ratio in between those two. And also we consider all the instances. So approximation algorithm has been designed since 1980s or even earlier. And however, in most of the in most of the algorithm that we have seen so far, and the way of calculating the ratio, the approximation ratio, is as below. So we just take a maximization problem as one example. So the objective is to prove that the optimal solution and the algorithm solution, the ratio is bounded by a value alpha. So this is our objective. Since like we couldn't find out the optimal solution in polynomial time, subject to the assumption p doesn't equals to np. And also if you enumerate all the possible solutions and find out the optimal solution and use that to calculate the optimal value, that doesn't help us because your algorithm, which is to enumerate all the possible situations, the algorithm doesn't take any insight of the problem and it doesn't help us. So instead of trying to directly calculate the ratio, we find out in an upper bound of the optimal algorithm such that the ratio between the optimal solution and our algorithm is bounded by the upper bound of the optimal solution and our algorithm. So the upper bound is the key component when we design approximation algorithms, since like the upper bound of the optimal solution could be acted as a bridge to connect the optimal solution and algorithm, so that we have upper bound over the algorithm, right? So the upper bound is related to the optimal solution here, but it's also related to the algorithm as well. And then if we could have an algorithm, right? If we could find out an upper bound, which so that the ratio is bounded by alpha, then we get our approximation ratio. So this is the way for us to analyze the approximation algorithm to whose approximation ratio is alpha. So for the minimization problem, the way is the similar. You just reverse the order of, you find out the lower bound and reverse the order of these ratios. So however, I want to point this out. The reason is that for classical algorithm, approximation algorithm design, this is the way that we are taking. And this is the different from the last, the quantum approximation algorithm that I'm going to introduce at the end of this presentation. So this is the, they consider the approximation ratio from two different approaches. So in order to illustrate the algorithm design approaches using the classical computers and the quantum computers, I'm using NP-hard problem as one example. So this is the problem that has been studied for quite a long time. The problem is called maxcat. So the input is an undirected graph. with non-negative weights and for each edge. And the goal is to partition the vertex set into two parts. So U and W as the vertex set. And the objective is to maximize the total weight of the edges with both of it is their endpoints in these two sets, U and W. So a cut, that means like for the max cut, that means like we are going to look for a cut, a set of edges, such that if you remove these edges, then the graph is partitioned into two or more pieces. We would like to see what is the total weight of this cut. And I apologize that this figure is in a wrong order, a direction. So, but as you can see, like we have A, B, C, D, 4 vertices with the weights 10, 3, 5, 4. So if you select these two edges, A, B, and DC as the cut, and then remove all of them, then we have two parts. And one part contains AD and another one, which is DC. And the cut weight, which is 10 plus 5, which is 15. So this example shows that what is the max cut problem asked us to do. And the problem is proved to be NP-complete. And it remains NP-complete if we consider the unit weight graph. So like all the edges are with the same weight. That means like we want to maximize the number of the edges in this cut. Even in this case, that the problem is still NP-hard. And and even if all the vertex has a degree no more than 3, and the problem is also NP-hard. So it has been proved that the problem is hard. And I want to mention here that is the I couldn't remember the author's name. So there's the one paper, maybe Yanakakis, I couldn't remember that. So he proved that for the planar graph, finding out that the max cut is polynomial time solvable. So that means like for the general case or for some special case that the problem, the max cut is still hard. So after introduce the basic concepts and the problem, then we are going to introduce the algorithms. The first algorithm is quite simple and quite intuitive and is easy to understand. But it gives us some of the power of designing classic algorithms and the way of finding out the approximation ratios using the technique that we just mentioned to find out the upper bound of the max cut to bridge the optimal solution and the algorithm solution. So here is the first algorithm. It's a randomized algorithm. Say like this is the bold algorithm such that the algorithm itself doesn't rely on the problem quite much. And also the algorithm doesn't introduce much of the insight whenever you study the optimal solution. Even we have no idea what is the optimal solution for this max cut problem. We just blindly, randomly assign the vertex in the set into these two sets. So like for each vertex V, and we place V into U independently with probability a half. So and then we return the two sets U and W. This is the simple randomized algorithm. So Paul Erdos proved that the algorithm itself is two approximation. Of course, that the approximation ratio, this concept, was not termed at that time. But Paul Erdos shows the relationship between the algorithm's performance and the upper bound of the optimal solution. So the running time is in linear time of the number of vertices in this set. And of course, this is the for loop, right? So here we have an indicator variable to indicate whether an edge is included in the cut or not. So we have an indicator variable. So the proof is pretty easy and straightforward. So let Z denote the total weight of this cut. So the expected value of the cut is the summation of W, which is the weight of these edges, and the expected, which is the expected value of this indicator variable, whether the edge is included in the cut or not. So the expected value of the indicator variable is the probability that this indicator variable is true. So that is the probability that the edge belongs to the cat. So since like we pick up these two vertices independent with the probability and half, so we have a probability a half to make this edge into the cat, and then we get 1/2. And here is the proof. Sorry, here is the upper bound of the optimal solution, which is the sum of the total weights. That means like the optimal solution, optimal algorithm cannot have a total weight more than the total weight of the edges in this graph. And therefore, the expected value of this cut is at least half of the optimal solution. So here's the randomized algorithm, and we have the randomness, which is just like we find out we place the vertex with the probability half. So the randomness is internal to the algorithm. And using the standard de-randomization technique, we can remove this assumption. We can remove that the randomness, which is internal to the algorithm, and still get the algorithm with the performance no worse than a half. So this is a standard de-randomization procedure, which is to remove the randomness internal to the algorithm. If we understand that at any time when we make a decision, and that time when we make a decision like here, and for this step, we can replace using the conditional expectation, and then we can remove the randomness using the following way. So for here, that for each vertex, right, instead of putting it into a vertex U or vertex W based on the output of the randomness, and we will calculate the expected value, the expected conditional value subject to the vertex is put in U or the vertex is put into W. So we have two options, either U or W. So we would like to, what is the conditional probability or conditional expected value if we put the vertex into U or the vertex into W? If putting it into U is better than putting into W, we put it in U, otherwise we'll put it into W, and then we still return the cut. So this is the trivial de-randomization practice. Then it is here is the pictorial illustration. So initially we put a V1 into the U set. So whenever V2 comes, that we look at what is the expected value of Z given the condition that V2 is put into U or V2 is put into W. So if V2 is put into U and then the expected value is decreased, right? Like this one. And here is the graph as an example. If V2 is put into W and the expected value is increased. So based on this ratio, so we put a V2 here. And then we consider the next vertex, let us say V3, and if we put a V3 here, right, and then V3 and V1 are in the same set. So the total expected value is decreased. And it is decreased with the probability half, and also we take the total weight into account. And if we put a V3 into the set W, and then the expected value is increased, right? So it depends on the W13 and the W23, and then we would like to determine where we put a V3 into this set. So in this way, we just de-randomize the both randomized algorithm and get algorithm whose performance is no worse than the randomized one. So here's the trivial result. It's just more like a assignment problem. So like our algorithm 2 is the same performance as the algorithm 1. And the total running time is order of V squared, the number of vertices squared. Since like we need to look at the conditional probabilities, and for each conditional probability, we need to look at all its incident edges, and therefore it takes more time than the bold randomized algorithm one. So the proof is also a classic, the proof also relies on a classic technique such that you consider the probability that all the vertices right? Either in U or W, we are using BI to denote either U or W. And then we take the conditional probability, right? And we know that assume like it is put into U, so this probability is larger. And if this probability is larger, and definitely this will be larger than expected value whenever you choose half probability or safe probability for the case that the vertex VI plus 1 put into U and W. So this is the same performance and the algorithm, polynomial time algorithm, with the approximation ratio I have. So I'm going to, sorry. I introduced this algorithm just to practice the idea of analyzing approximation algorithm we just mentioned in the basics of this presentation. So we know that this is the algorithm, and this is simple to implement. And this, when we calculate the approximation ratio, we look for the upper bound of the optimal solution, and we use that to bound the ratio that we are seeking for.
Faye, there is a question in chat. I don't know if you can address. Raphael is asking about conditional probabilities.
Okay, so okay, good. So let us look at the. Give me 1 second. So I'll go back here. Okay. So this is the expected value of the total weights of this cat, given the condition that V1 is in U or W. V2 is, this is the inductively, right? Initially, we put V1 into U, and then based on the algorithms we have shown here, and then we put V2 into W. And the V3 depends on the condition that whether V1 and V2, whether they are put into U and W. So V3, whether we put it into U or W, this is the conditional situation that we need to calculate. We need to calculate the conditional probability of putting V3 into U and putting V3 into W. So the calculation here is that if we calculate the expected value of the total weights of this cat, right? So this one equals to, this is just the conditional probability definition, right? This probability is the probability that you put the VI plus 1, the next vertex, into U times the probability that all of the vertices follow the decision of putting VI plus 1 into U. And also times the probability you put a VI plus 1 into W times the probability you put all the vertices as you plan to put into W, right? And if you sum up, remember that if for this probability, the randomized algorithm, the first randomized algorithm, this probability is just a half, and this probability is also a half. So we have the weighted, we have the expected weights of the vertices V1 to Vi. They are assigned to the vertices, they are assigned to the vertex set as B1 to Bi, right? This is the value. Okay. So this is the value, expected value for the algorithm 1, the first randomized algorithm. But for us, when we de-randomized, then we put the Vi plus 1 into the set, given the condition that this expected value is larger than give the I think that, given this one is larger than to put the VI plus 1 into the other one. For example, that if VI plus 1 put into U is larger than VI plus 1 put into W, right? If this expected value is larger than this expected value, and the second algorithm choose this value, and therefore the second algorithm's expected value is larger than this one. Is it clear? Okay.
Thank you. Yes, thank you.
So this is the first algorithm that we introduced. That is, I think that the motivation of introducing this also is not to provide a complicated algorithm, just to provide a sketch of designing approximation algorithm and analyzing the approximation ratio. And then we look for the second algorithm on classical computers. And before we introduce the algorithm, we introduce a few concepts. But these concepts may be, you may not memorize these concepts since like they were introduced in the linear algebra class that you may have taken quite a long time. But we just review such little materials, and then we will see the algorithms, and we will talk about the idea of designing the second approximation algorithm based on these concepts. The first is about the positive semi-definite matrix X, right? A semi-definite matrix X is positive semi-definite if and only if for all the vector Y, you have the transpose of Y times X times Y, which is non-negative. So this is the definition. So in the linear algebra textbook, for this, if you have a matrix which is n by n symmetric matrix, then the following statements are equivalent. It is the matrix is positive semi-definite, and it has non-negative eigenvalues. It can be decomposed into matrix V transpose times V, and also for some lambda, which is eigenvalues and vectors W such that W transpose times W is 1, and the W transpose W i's transpose W I is 1, and the W i's transpose W j is 0. So this is for all these four conditions that they are equivalent. That means like you could use any one of them to define the positive semi-definite matrix. We may not use all of them, the effects, but we would like to use the item 3, the bullet 3 here, to show one result on the next few slides. So what is the semi-definite program? So we know the linear program and we know the integer program. That means like we have a linear or constraints over the variables. A semi-definite program is similar to the linear program. It is the mathematical program with 4 components. First of all, you have the variables, xij, and you have the linear objective function, either to optimize or minimize. And you have a set of linear constraints over the xij. And the key component is that the xij, or the variables, they consist of a matrix, which is the semi-definite. So here is the semi-definite program example. That is the linear constraints over all the variables and the linear constraints of all the variables. But the variables consist of a semi-definite matrix. So let us proceed. This is just a definition. So we will proceed. So if you have concerns about these definitions, then we could talk about them later. And then we proceed to the algorithm. Okay. So what is the significance of having the semi-definite matrix, which is different from other? Well, what is the necessity that we have to introduce the semi-definite matrix, right? The semi-definite constraints, that which is in the semi-definite program, they could be interpreted as infinite class of the linear constraints. So if they could interpret it as an infinite class of the linear constraints, then we could have a nonlinear feasible region for us to find out the variables or find out the objectives. So here is the one example, right? Assume like we have C1, which is a linear constraint. C2 is a linear constraint. C3 is a linear constraint. And these 3 constraints, they are linear ones, right? We have linear ones. But assume that for this feasible region that there is the nonlinear curve, like a C4 like this, nonlinear curve like C4 like this. So how can we describe the C4? How can we describe C4? So for C4, you could think about that this is you have infinite class of linear constraints like CA, CB, C3, etc., etc. So you have many linear constraints like lines to estimate the curve as much as you can. So if you have an infinite number of linear constraints, right, how can we argue that the infinite number of linear constraints could be represented by the semi-definite matrix? So here is we get back to the definitions here, right? So look at here. So for all the vectors that y transpose times x times y, this is non-negative. So they could be, this is the semi-definite matrix definition. So this condition is equivalent to say like for the matrix X, you can decompose it into V transpose times V. So for all of these V's, you can think about that each column of this V could be regarded as one constraint, one linear constraint with one set of variables, So this is the what you can have. So this is the one linear constraint. You have a set of variables. This is another linear constraint where you have another set of variables. You have infinite class of these linear constraints. And for all these classes, they could be represented by the vectors in the matrix V in the previous definition. So this is the one pictorial illustration of the necessity of having semi-definite constraints. So for the semi-definite program, and they could be solved in polynomial time, but only within additive error of epsilon. You cannot get the optimal solution like the you cannot get the optimal solution in polynomial time, since like you have infinite number of such constraints. But you can approach to this optimal solution as much as you can with additive error, which is epsilon. So this is the significance for us. And also we could rely on the semi-definite program to find out the solution. And since like we could find out the optimal solution, then we could use that one as the upper bound of the optimal value. Okay, so let us proceed. So a related formulation is called vector programming, and this is related to the semi-definite program. So a significant conclusion is that the semi-definite program and the vector program, they are equivalent. They are using different forms to represent the constraints, but essentially they are the same. And for the vector programming, that is says like for all the variables, they are vectors rather than real numbers. And also all the constraints could be expressed as linear constraints of the inner product of these vectors. So still that we have the maximization or minimization as our objective, but for those variables that they are not real values, instead of they are vectors. So for all the vectors and the vectors, whenever we are dealing with them, we consider the inner product of these vectors. Okay. So this is the vectors program. So the proof is pretty straightforward as well. So you can look at the linear algebra textbook to find out this proof. So the vector program is the one that I like to use to formulate the constraints. Since like for the semi-definite programs that I have to check whether it is the semi-definite, but this will be easier for me to formulate a problem. Okay. So we get back to the max-cut problem, and then we try to look for the formulation of the max-cut problem. Recall that if we are using the integer program to formulate the max-cut problem, so we are using the indicator variable y sum I to indicate whether the I vertex belongs to U or not. For example, +1 says like I belongs to U, -1 says I belongs to W. And whenever U and W, whenever U and I and J is an edge cross this cut, so we need to contribute the Wij to our objective. So as you can say, like if both of them, Yi and Yj, they are -1s or +1s, and this product is 1. So this will be, this edge will contribute 0 to the objective. But if they belong to different sets, like U and W, so 1 and -1, so this is the -1, 1 minus -1 is 2. So 2 over 2 is 1, so it contributes to objective Wij. So here is the integer program of the maxcut problem. Well, the good thing is that for here that you have the variable y and yj, you have the product of these variables, and you would like to relax these variables and using a vector to replace the integers, positive one or negative ones, and then you have the corresponding relaxation of the integer program, like here. So we still have the vector vi, and then vi and which is the inner product is 1. So 1 minus vi and which is inner product. I spent much time on this one, but let me complete this part. So for the integer program, so you map 1, right? The integer of y and yj, you map it to a vector. This is the vi and vj, this vector. You could make the vector like this, or you could make the vector like this. And you can check that both of them are feasible solutions of this vector program. So here's the key of designing the algorithm. So for the integer program, we know that it's really hard to find out the solution in polynomial time unless p equals 20p. So we are looking for the relaxation, which is polynomial time solvable with additional error bounds. But for here, that whenever we get the vector values, they are not the integer values. We have to convert the values back to integer values in order to create a feasible solution to the maxcut problem. So this step is called rounding technique. Rounding technique has been used extensively in designing, in analyzing and designing approximation algorithms. So I will go a little faster for this tedious analysis. But I would like the idea is that you would like to, whenever you have all the vectors in the unit sphere, and then for these vectors, this is all the value that you get from your vector program. And now you would like to map these vectors into some integers in order to determine whether the vertex 1 belongs to U or W or not. So the algorithm is that we just randomly pick up a hyperplane to separate those vectors. And if the inner product of these vectors, if the inner product of these vectors are positive, they put into the same set. Otherwise, they put into different sets. So the algorithm, right, which is as below, which is that we first calculate the vector program and find out the solution. And this step is polynomial time solvable, and we only get a bounded error. And then we pick up a random vector. This is similar as the randomized algorithm that we have introduced. And based on this random vector, right, we calculate the inner product of the values that we get. And if the product is positive, we put it into U. If the product is negative, we put it into W. Okay. So this is the semi-definite program-based algorithm. The algorithm itself is a 0.878 approximation. The running time, which relies on the step you calculate the vector program. And people are using the integral point method to calculate the solution for those vector program. And this is the total running time for that solution. So here is the pictorial illustration about the analysis. So like if they belongs to the same set, right, they put into U. If they belongs to the different set, they put into W. So what is the probability? Since like the vector is selected randomly. So what is the probability that their inner product is positive, right? So it relies on the theta. So this is the total probability should be this part and this part over the total size of this circle, which is 2 pi. So it's quite easy to see that. So, but and then you know that the total probability that this edge is in the cut will be 1 over pi cosine V and Vi is inner product. And through some calculation, then this is the result you get. I don't know, so let us skip this proof. And then we know that for the approximation algorithm, on classic computers, if the unit gain problem, if this conjecture is true, then we couldn't get a better approximation ratio than the approximation ratio 0.878 unless P equals to NP. So what does it mean? It means like, it's almost to say like, if the conjecture is true, that this is the best approximation algorithm that we can get, no matter whether you are using the classic computers or quantum computers. So, so I have 15 minutes or so to introduce the last quantum algorithm. So I'm going to introduce the last algorithm dealing with the max-cut problem on quantum computers. So when we design quantum algorithm, here are the 3 steps that we need to take whenever we design algorithm on quantum computers. So unlike the ones that we consider the classic computers, we consider the steps sequentially. And for quantum computers, that the first one is that you get an initialization. So if the input string is X, then you generated the X qubits along with several ancillary qubits, which is initialized to be all 0 state. Okay. So this is your initial state. And at any time, you could add you could add the gates, the quantum gates, to manipulate the system states, which is the superposition of all the qubits. So you have all these qubits, and then you would like to consider to add some operations over these superpositions of these qubits. And the last one, so if you feel like this is the state that you're looking for, and then measure some of the qubits, and then generate the solution. So you could measure it, right? If you could reject it if you get it up to 0, accept it if you get it up to 1. This is for decision problem. But for the optimization problem, that you could define your rule to whether you accepted the value or rejected this value whenever you measure that. And after the measurement, then you couldn't get the superposition for that qubits. So this is the 3 steps in designing quantum algorithm. This is quite, at least to me, that it is quite quite sketchy. So we'd like to see a concrete algorithm in designing quantum algorithm, a concrete algorithm to see how to design quantum algorithms. So let us, the first one is that when last semester, when we first considered the designing quantum algorithm, I started from the way of mapping the classic algorithms to the quantum algorithms. We do nothing, just would like to map it and implement it using the quantum circuits. So for the classic randomized algorithm, we put every vertex into the set U, right, independently with the probability B. So we add Harmon circuits here and then measure that. So this is that we do nothing fancier, but this is the, we get an algorithm with 2 approximation ratio. Right? This is pretty trivial. But when I read the textbook, I realized that maybe this is not a good way, since like if the graph has more than 100 qubits, then you couldn't implement the algorithm on the current quantum computers. So like based on some constraints that you cannot have more than 100 qubits. Right? And instead, that whether we could reuse the qubit for the algorithm by running it multiple times. And if we do so, then based on the definition, it doesn't seem like it is the quantum algorithm anymore, but it is just the issue that I was wondering before, okay? And also that for such kind of algorithm, you cannot take the derandomization step. Like what we did for the first randomized algorithm. Okay. So in designing the approximation algorithm for such kind of NP-complete problems, then there is only one framework that I have read so far. And also people, at least in 2018, people claim that this is the only framework that people are designing approximation algorithms. That means like the algorithm has the following framework. The first step is that here you have your objective, right? You translate the objective into the equivalent quantum Hamiltonians. My understanding, which may not be true, may be incorrect, that is that you would like to transport into the initial state, and this initial state is the randomized state. And then you would like to manipulate this superposition of this state by applying the matrix operator. And such kind of matrix operator, so you would like to apply it for P rounds. So you run it for K times. So you apply the matrix operator beta sub K and gamma sub K. And the beta sub K and gamma sub K will be introduced in the next slides. So it's more like that you start with the initial station and then you apply several matrix operations over that. And you apply it multiple times and then you stop, measure that, and then you generate the output. So the framework is pretty straightforward, but the algorithm is a little, at least to me, it's not that easy to understand. It's not that straightforward. So the algorithm is that you get the initial state and then you run P rounds, and then you return the expected, you return this value as the expected total weights. And the reason is that I don't know actually, right? What is the matrix operator applies here? So I try to read the documents and try to read the underlying geometric interpretation to deepen my understanding. So this is what I got. So the objective as what we have seen, which is 1 minus the sigma u and the sigma v, is to find the max eigenstate of the sum of local Hamiltonians. So I couldn't find out these concepts or some of the deeper discussion of this one from the books that I have. So I like to try to see what is the interpretation of this one. But the proof of this paper shows like for the U and the V, if the weight of this edge contributes to the objective, and it contributes to objective, which is like this, subject to the graph, right, which is the 3 regular graph. 3 regular graph means like for every vertex, there's only 3 edges. So here is the dilemma bothers me, right? Williamson and Schmorse proved using the vector program that the semi-definite program generated the approximation algorithm with the ratio like this. But let us say almost 10 years later that Fahy proposed the framework showing like the quantum algorithm, which is worse than the classic algorithm in terms of the approximation ratio. And so based on this concerns that currently I'm working as that I'm trying to implement the algorithm 3, which is the vector program on quantum computers, try to define a quantum circuits for this one. However, based on discussion with my collaborator from another school, she told me like that people have tried to implement semi-definite program on quantum computers. But till now, I haven't found out any published work yet. So I would like to study the vector program and the quantum circuits in order to further understanding that what is the key component in designing approximation algorithm on quantum computers. At least for now, that we know that to prove the approximation ratio for the quantum algorithms, it doesn't rely on the upper bound of the optimal solution. So, so let us get back to the picture that we have discussed at the beginning of this presentation. We know that on classical computers, we look for polynomial time algorithm whose performance is near optimal and the gap is defined by the approximation ratio. But in designing the quantum approximation algorithm, that means like we run multiple rounds. P is the number of rounds that we run. So whenever we run multiple rounds, that the value returned from the quantum computers is close to optimal. close to optimal. So the trace of the algorithm, right, based on the number of runs is getting here. And also the running time of this curve is getting worse and worse. So nobody has, at least based on the papers that I have read, nobody has shown that what is the curve looks like. And where is the best point that you need to stop in order to further explore the approximation ratio. So what is the balance between this one? And also for the algorithm that has been given here, apply those matrix operators. So whether we could get some information along this process in order to help us to find out better matrix operators. So this is the question that I'm working on. So essentially, I will try to answer the question from the unknown input distributions, whether we could construct some of these algorithms such that for special instances, we can find out the optimal solution using a quantum algorithms. But just run a few runs and don't get the optimal solutions. But this algorithm must be for some special instances. So I'm still reading the document, which the one that I'm not presenting here, and also some of the online learning papers on classic computers, and try to bring them back and then integrate them together to find out the answers for myself. Okay, so that is all my, okay, well, Micah gave an answer, which is quite, I think that is the easy thing for physicists, but I don't know this one, but thanks, Mike, I will read it. That is all my presentation, and thank you so much.
Thank you, Faye. Virtual applause. I guess we have time for a few questions if anybody wants to comment.
Faye, can you go back a few slides to where you did what you thought was the trivial quantum algorithm?
This one, right?
Yeah, I just wanted to take a look. Why is it that this doesn't end up working exactly like the classical algorithm?
Okay, so for here that for each vertex, right, you build up some V qubits and V classical bits. And for each qubits, then you add a Hartman matrix, right?
Yeah.
And then whenever you measure that, you can get a value in the range from 0 and 1. And then let's similar like this. So if the value is lower than a half, then you put it U. Sorry, you put it V U. Yeah. If it is larger than a half, you put it W.
Oh, I see. So this is just a matter of there being actual equal probability, and it's not like you're specifically placing half of your vertices in one and half in the other.
No. Actually, the implementation is more like that. So you have the qubits, and then you measure it, you measure it, you measure it. There's no entanglement of all these qubits. There's nothing fancy here. Okay, and whenever you measure it here, and then based on the value here, you determine whether to put that vertex into U or W.
Okay, I was wondering if maybe it makes more sense to, well, no, I'm just recreating the classical algorithm, the quantum circuit, never mind.
Faye, I just wanted to ask about that, the Hamiltonian procedure at the end. So I understand that basically you're still understanding this yourself, but are you guaranteed always to have a local Hamiltonian in this case?
Yeah, the paper says like you can get a guarantee, right? So, but you, as I have mentioned, like I don't know exactly what is the meaning it shows here. So Mike says something in the chat window. So I need to have a better understanding about this one and get back to you. But this is what I learned from the paper. Yeah. Actually, personally, I would like to think about this as my understanding, which may not be correct. My understanding is that assume like you have a system of all these superpositions. Then you apply this matrix operators over that. And this is the more like that you find out, you know, it's iteratively you calculate the superposition, right? But I don't know, I don't have a geometric interpretation of what is the operation looks like and how it results to the local Hamiltonian. That is the thing that I'm having to figure out clearly. Another one is that for this paper, it shows that it gives a better interpretation, but maybe Mike knows about this one. I don't know. It says like based on, it looks like that there is the fermionic view of this manipulation. I don't know exactly what it is. I'm still reading that paper and looking for some background knowledge to deepen my understanding about it.
So I guess, Michael, the question is whether you can shed some insight on what fermionic view could mean in this context.
Excuse me. Fermionic, I'm sorry, what?
Yeah, that was the title of the paper, right, Faye? So it was fermionic view.
Oh, I think that just means, I mean, they're probably just talking about, I mean, I'd have to look at the actual paper. I haven't read it. My guess would be that they're using some sort of fermionic Hamiltonian or something in the QAOA procedure, but I really don't, I don't know what the fermionic view would possibly indicate.
So Faye, what I didn't understand is, are they claiming that at the end, when they're using this Hamiltonian operation of converting the problem into this fermionic, are they claiming exponential speed up as a result or not?
No.
No.
There's no. Eventually, they have a number of p as the upper bound of the rounds that you make. So whenever p is larger, and then the running time, like the step 3 and 4 will be, the running time will be growed exponentially. So the algorithm itself, if you have unlimited p, then you can reach to the optimal solution, but the running time is also exponential 1 as well.
Okay. All right.
So they consider the case that p is 1. Right? They have an algorithm. So if p is 2, then the algorithm performance is getting better. Right? But if p is large, and then the running time is also expensive. So they didn't want to go beyond that.
All right. Are there any other questions? We're a little bit behind. So I guess if no more questions, then thank you everybody for